So I say the language, but people in here who actually actively work with ML are probably aware that ML is not just one language, right? So there are at least two languages in there. So the one thing is the obvious core language, familiar from other functional languages, so where you have functions and records and can define various computations. But in ML, you also have a whole different level, which is the module language. So in the module language, you also have this thing like something like functions, which are just happen to be called functors. You have a form of records, which are just happen to be called structures. And so you can express very similar things. The syntax is completely different, but structurally it's pretty much similar to some of the things you have in the core language. And if you want, there's even like a third kind of language hiding in there, which is the language of type expressions, where you can also express some of the same things. And again, yet again, the syntax is entirely different for no obvious reason. So complaining about syntax here in this audience, of course, everybody's aware syntax doesn't matter, right? Only semantics does. So, but it's not just syntax. Going back to like what you can do on the core level, well, there are these various ways. For example, you can do parameterization, right? So you have conventional functions, you have polymorphism, which is basically parameterizing a value over a type, and you also have type constructors. And then you have the module level where you can parameterize modules over modules. That is what a functor is all about. And since a module, though, can contain any of the other language entities, this allows you actually to express all these kinds of parameterization as well on the module level. It also happens to allow you to express the fourth kind of parameterization, like the missing dimension of the lambda cube, if you want, which you might think is not really relevant in ML because you're not in a dependently typed language. Turns out it is to some degree with applicative functors, but I won't get into that here. The main point here is that you really often have a choice between like at least two ways in which you do parameterization, and this is often not an easy choice, and it has different trade-offs, and it of course has pretty significant implications downstream what you choose. And that gets me to the next kind of issue with modules in ML, which is that they're second-class citizens, right? So I already said you have this completely separated language layer there, complete stratification, both in terms of syntax and mostly as well as semantics. And there's a trade-off usually, like which level you choose. So on one side, you have modules with this fancy, very expressive type system. On the other hand, you have the core, which, for example, gives you a lot of convenience, for example, in the form of type inference. But more importantly, also, the core level is computationally much richer than the module level. There are lots of stuff you can't do with modules because although you have functors, you don't have recursion, for example, or conditionals or anything like that. So on the module level, you cannot actually compute. You cannot compute modules, or you cannot use them as data or pass them around in any way. And that is, of course, a limitation that many people have observed before, and for which a remedy was proposed long ago, which is the notion of what I call here packaged modules. So that was originally invented by Claudio Russo in the late 90s, and he implemented it in Moscow ML. After that, various other papers and languages followed that. Most recently, OCaml, where actually this notion of packaged modules sees quite some use in practice already, from what I see. But I should stress here that I call that packaged module, although it's usually informally called a first-class module, it's not actually first-class modules. It's a somewhat more limited thing, and we will see later a couple of examples of that. So we have the second-class system here, and I'm a politically inclined person, so I don't like the situation. I don't want that, right? I want a classless society. So I want a real language with real first-class modules, where modules are first-class citizens, and I get the full expression of that. At the same time, I don't want to give up anything. So I really don't want to lose any of the expressiveness I currently have in conventional ML. So computationally, for example, but also not any of the convenience like type inference. And of course, I want a society with style. So all this syntactic incoherence I showed on the first slide, I would rather not have that. And that's the idea of 1ML. Basically, 1ML is the idea of collapsing the core and the module level into one consistent language. And in most of the time when you see papers or languages trying to do something like that with first-class modules, then the approach they take is you have some core language already, and then you try to add module-like constructs to it in kind of a first-class manner. And this usually never really works well. You always run into restrictions because more or less modules are still like an afterthought. So that's not what I want to do. I want to do the opposite. I start from like a complete, fully expressive module language and just add core-like constructs to that and see where that takes us. And more concretely, I'm basing this on our earlier paper on the effing module semantics, and where we basically just collapse the two language levels. But as you can guess, this is not going to be completely seamless, so there will be some challenges we have to deal with. Okay, let's get a bit more concrete. This is the syntax of 1ML, or let's say it's actually the explicitly typed fragment of 1ML. And it's more or less like a simple functional language. So you have functions here, you have some kind of record or structure if you want. Functions are also functors. You have the usual constructs that you see in a core language, like just a representative here is like booleans and conditionals. And you have constructs from the module language, like the ceiling operator, for example, you know from ML. And similarly, on the type level, this is reflected in the way you would expect. So you have record types, you have function or functor types, and I distinguish here two kinds of arrows, which are like the pure and the impure functions, which I will get to a little bit later. And you also have the kind of signature-like refinement constructs that you know from ML. And then you have this maybe a little bit more weird thing here, which is the type. And correspondingly, on the expression level, you have this expression that wraps up a type as a value. So what's up with that? Remember, we are in a language with modules, with first-class modules. And modules can carry types, right? They can contain types. So in conventional ML already, you can express like a module like this. So this is a structure that contains a type component that is defined as int, and its signature would be something, for example, where type T is an abstract type. And what I want to do is I just want to decompose this thing into simpler primitives. I want to treat that as syntactic sugar for a structure that just contains a regular component, a value, which happens to be like atomic type thing. And this then has the type. And when I decompose it like that, I can just view that as a wrapper around the anonymous thing. So I have this as a value, and in the literature, this is often called an atomic module, and it has this type that I write type here. So this may be surprising at first, unless maybe from the dependently typed language perspective, but in ML, but it's actually pretty common in the literature on ML modules already, where this kind of thing occurs in intermediate languages. And really, it doesn't give you anything new. It's really just decomposing some syntactic construct into more orthogonal primitives. So it's really just a syntactic cleanup. And here we make it available in the source language. And this carries over to type constructors. So when you define a type constructor in 1ML like this, I really want to treat that simply as syntactic sugar for a functor. So point is just a function or a functor, whatever you want to call it, that takes a type and returns a type in this atomic manner. And similarly, where you would specify a type constructor like as an abstract type in ML in a signature, this again is just syntactic sugar for a functor signature. So all these notions, functor, function, type constructor, are now unified into one thing. There's one caveat, though, which is to make this work, you expect that a type constructor, even when it's abstract, is like reflexive, right? So if I apply point to the type int twice, this should yield the same type. If you're familiar with functors in ML, then you know this whole deal with generative versus applicative and so on and so forth. Cutting that short, the issue here is to make this work, you need a notion of applicative functor. So a type constructor really has to be an applicative functor. So this language here has both applicative and generative functors, and that was the two kinds of arrows I showed earlier. They correspond to these two notions. Okay, so just to give you an idea how a real program would look like now, with a little bit more syntactic sugar, which I'm not going to explain here in detail, you can now write something like this, which should really look like very familiar from an ML perspective. The main difference being that you're defining like a functor here and a signature, but you don't write signature, you just write type. It's just a type. But it's a type that contains type members itself. So conventional stuff you can still do, but you can also do new things now. So you can compute modules. So you can simply just write a conditional over a module. So the standard example from literature is picking a map based on the size of your data set, for example. I should mention this is something you can already express with package modules, though. So for example, in OCaml, you can express the same thing somewhat like this. So this works, but I guess I hope we all agree that this is kind of not what you want to write in practice. So this is a bit more like direct. But you can go further. There are now things that cannot directly be expressed anymore with package modules. So here's an example which maybe the easiest way to read this is as this signature thing defining a type class, basically. It's a signature that's parameterized over the type C and defines some methods on it, and also two types, which in the Haskell world you would call associated types. And then you can write a function that takes one of these things. So if you know Haskell, you can read that as an explicit instance argument, if you want, the C thing that has the signature, and we can write a result type for this thing where we just refer to these associated types. So this is something you obviously can't express like that in ML. Not even with packaged modules, but you can work around that in some kind of pretty tedious way by pulling out all the abstract types as separate arguments and using fibration and so on and so forth. But this doesn't really scale all that well. In particular, it doesn't scale to an example like this one where the thing we parameterize over is actually of higher kind. So here, this just doesn't work in ML anymore, even with packaged modules, because we have higher kind of polymorphism, which doesn't exist in ML. Whereas in 1ML, this just falls out naturally of the fact that everything is basically just a module. Modules are higher order, so you can just express this. You can just write it. Okay, so this is all nice and elegant, or so I claim. I hope you agree. You may wonder why this wasn't like the case always, why this wasn't done before, why modules are second-class citizens so far. And so there are various reasons. There are pragmatic and historic reasons, which I won't go into here. I guess like Dave sitting over there can probably tell far more things about that. I want to focus on the technical reasons for that. So there are two technical reasons that you find in literature why modules are second class. The one is decidability, the other is type inference. So regarding decidability, it's a well-known result from literature that if you have a language with signature matching where you allow an abstract type to be matched by something that is itself a signature that might in turn again contain abstract types, then this leads to undecidability. So that's a result by, by Harper and Lillibridge in the context of their translucent sum calculus. And it also pops up in OCaml actually on the module level where this leads to undecidability of the OCaml type system, or the module type. So you may regard that as more like an academic concern, but of course type inference is a more practical concern, and it's non-obvious how you can do type inference in a language like this. I should also briefly mention two things that are non-issues here, which often pop up in the ML module literature, which are the notions of phase separation and the avoidance problem. Don't worry about it. It's basically, it's not an issue here, because by us starting from an actual working module system as the basis, all these problems are already solved, particularly in the effing semantics. So we don't really have to worry about it. Okay, so how do we address these two challenges? The main idea here is, or the main notion that we need here is predicativity. And again, this is not really a new idea, not even in the context of modules. It already pops up like in an old paper by Harper and Mitchell where they have this XML calculus for formalizing ML. And the idea is you separate the universe of types in two. So you have the large one, which contains all types, and then you distinguish small types, which are basically monomorphic types. Or in other words, types that don't contain the type themselves. And then you impose one key restriction, which is that only small types have the type. And this carries over then to signature matching in the sense that you can only match an abstract type with a small type. And it turns out that is all you need. That's all you need. Like the whole thing in ML about stratifying the language is having completely separate syntactic layers and semantic layers. Really, it all boils down to be a crude, super verbose way to enforce predicativity. And here we replace that with a simple semantic distinction in the typing modes. What about type inference? We can reuse the same distinction, actually. So we just say, okay, small types is all we infer. We don't infer large types, period. And then you have one other key observation when you look at the effing signature matching rules and specialize them to small types, then they degenerate almost entirely to type equivalence. So you can actually piggyback the subtyping algorithm and on small type turn it into a unification algorithm. There are some tricky things to worry about there, but it's in the paper if you want to know the details. So I'm not going to lie to you. This is not a complete inference mechanism, of course, not even for small types. There are a couple of ways in which it is incomplete, but my main observation and claim here is none of this is new. All these incompletenesses actually already, exist in conventional ML, like in standard ML with records, and this value restriction thing also already exists. So you don't actually lose anything. My claim is, although I don't have formal proof for that, is if you have a program in SML and you just transliterate it into this language, type inference will still work. So you're just adding new forms of expressions for which you can't infer types, for which you have to add annotations, but you're not losing anything. So, sum up. Really, the essence of this whole module core level separation is just predicativity. And we can make that a semantic instead of a syntactic distinction. And that's the core idea here. And then you really have actual language with truly first-class modules and without losing anything, in particular not type inference as you know it. And also, this may now look like a dependently typed language, but really it's all still just system F omega. So it still has the simplicity semantically of F omega. And you not need any dependently typed theory at all. That's all. Thank you.
Hi. Hey. So there's this Reinhold-Meyer phenomenon where if you have the type of all types or types of values, you have this subtle non-terminism or non-termination without recursion. And I would guess that you get away from that by the small-large type distinction. Is that something that's been worked out or looked at?
Worked out. So you mean in the paper or? No,
in general.
In general, I don't know.
It'd be interesting to see exactly why the Meyer-Reinhold or Reinhold-Meyer phenomenon is avoided.
I don't know. It's a good question how exactly that relates to that. I don't have a direct answer, sorry. Okay.
So first off, I'd like to say I think this work is really beautiful. It really, speaks to someone who has worked with functors before. But I wonder if there's not still a place for module systems which are still syntactically stratified, maybe because they're not based off of function application, like they're using something else, like, I don't know, mixins or something.
Sure. I mean, mentioning mixins is actually a good point. So there might still be reasons to have a second-class module system. If you want to enrich it further than what conventional ML does, then this kind of unification might become even harder, like with mixins, for example. So, yes.
Thanks.
Hey. So, as I understand it, because I'm not fully familiar with the literature, the phase distinction is about separating type checking from the core language such that you can make sure that all your functor applications are well typed without executing code, right? But the one attribute that ML has, I think, is that you can do full defunctorization without executing core code as well. So you can statically know which module a given value is from.
Right. So this
is. In this, you lose that, right?
This is true in SML. it stops to be true as soon as you add package modules, for example.
Okay. So is there any future work toward making it explicit when that is or is not the case? Because you would think there would be some overhead associated with being able to look at a value to decide which
basically the observation here is what we now still call modules in here are basically just all the forms of quantification you have in the language, right? And so this really becomes the more general question of like, okay, when can I monomorphize? That's how I would put it. And there is work on that, but I mean, yeah. We now boil it down to a more general question.
Thank you.